This is Knowledge Engineering with Semantic Web Technologies, Lecture 4, OWL, Rules and Reasoning. And today we are going to start with the Web Ontology Language OWL. So, what is OWL? OWL, of course, is based on description logic. Description logics, we have already learned, are a fraction of first-order logic, which is in most cases computable and decidable. So, OWL appears in several variants. So the first one, it's the older one, OWL, is based on a description logic which is called join D. And as you might remember, all these capital letters that you see here in the name of the description logics stands for some kind of property of the description logic or for some kind of constructor that is available there. We will talk about that in a few moments. And the new version, it's called OWL2, of course, that is based on an extension of the old description logic, which is now called Schroik D. So this is the W3C recommendation since 2009, and we will refer in the future on OWL2. Okay, so what does an OWL ontology consist of? We already know that because we know description logic. So we have classes and we have properties, which in description logic often are referred to as so-called roles, and we have individuals, which are the instances of classes. So then next, important assumption, the so-called open world assumption holds. What does that mean? So just remember, the absence of information must not be valued as negative information. So this simply means if, for example, person A sits next to person B, this means that person A may also sit next to another person. And secondly, we also have no unique name assumption, which means then in the end, difference must be expressed explicitly. So person A possibly denotes the same individual as person D. If not, it must be expressed explicitly that person A is not the same as person B. So remember, for OWL, because it's a description logic, the open world assumption holds as well as the no unique name assumption. Okay, let's first have a look at OWL1 for historical reasons. So we know OWL is a semantic fragment of first-order logic, as being a kind of description logics. And also OWL1 exists in so-called 3 different flavors or variants. It starts with OWL Lite, which is a subset of OWL description logics, which is a subset of OWL Full. You see also the relation concerning the complexity here in a hierarchical diagram that starts at the bottom with so-called concept hierarchies. So these are classes which are subclasses of each other, and then more complex are on the one hand definitions made in RDFS and on the other hand OWL Lite. So these two are not necessarily compatible. Then we also have OWL description logic, which is more complex than OWL Lite. And if you combine the entire language expressivity from OWL DL, so OWL description logics, and RDFS, you end up in so-called OWL Full, which of course then is also backward compatible to RDFS. But it includes also the complete semantic expressivity of RDFS, which in the end means that simply because of reification, for example, then you also will have the possibility, or it will not anymore be decidable. So OWL DL, it's decidable. OWL Full is not decidable, simply because of its legacy down in RDFS. And then you see on top you also have first-order logic, and between first-order logic and OWL DL on the left side you also see the abbreviation swirl and riff, and this is nothing else but a rule language, which in the end we will also learn about later in the lectures. Okay, so this is the structure of OWL1. OWL2 is a little bit more complicated, but first let's have a look what the characters in the name join D really stand for. So first let's have a look at the axioms in knowledge bases of join D. So in the T box, in the terminological knowledge, we can express subclass relationships. So C is a subclass of D, and with this you can express hierarchies, therefore you have the letter H in your name. Then in the R box, which is the knowledge about roles, so for properties means you can have subproperty relationships. Again, for this stands the letter H. And you can define inverse properties. inverse roles, that's the letter I, and you can define transitive roles. For that, you have the letter S in your name. Then let's have a look at the A box, the assertional knowledge, so knowledge about individuals and their relationships. So you can, of course, define their facts for classes, so class membership. A is a member of class C. Or, for example, the property R connects individual A and individual B. Or you can say that two individuals are identical or they are different. Then you have class constructors to construct complex classes, and you also know them already. You have the conjunction, you have the disjunction, and you have the negation of classes. Moreover, you also have property restrictions, which can be universal restrictions or existential restrictions, with which you can define so-called strict bindings and loose bindings. We have already talked about that in the course of description logics. What is new? Because we have already talked about ALC, the most simplest form of description logics, here are the so-called number restrictions, for which the letter N stands. So in join D, you also have the possibility, in addition to everything we know from ALC, also to define number restrictions, which then, for example, gives you the possibility to define a class which is restricted by some numbers. For example, you can define a string quartet as being something which consists of exactly 4 members. Or you can here, you have number restrictions in the form that you can define something which sets limits, upper limits and lower limits to the members of a class. So these are number restrictions, but we will have another and more detailed look into that later on. So then the last letter that is missing, or one of the last letters, is O. You have the possibility to define so-called closed classes, nominals, or so-called enumerated classes. And there you simply define a class, or you have the possibility to define a class by class extension. You simply account or name all the individuals which belong to a class, and you put this into a class definition, and then you have defined a so-called closed class. And then, of course, you also include some data types. They are written in braces. Usually data type semantics is a little bit more complicated and not always part of description logic itself. So data types must be included, of course, when we are dealing with programming languages, and if we want to deal with integers, for example, with strings, with dates and all that stuff. So this is basically all the constituents of OWL1. Let's have a look at OWL2, the variant of OWL we are talking about. Also, OWL2 exists in different flavors, and again, you have the same kind of hierarchy. In the lower end, you have 3 different dialects, which are OWL-EL, OWL-RL, and OWL-QL. 3 different styles of OWL, which are a bit more restricted than OWL2DL, which stands again for description logic, or the description logics version. And these versions, EL, RL, and QL, have been defined for legacy reasons, and also because the complexity of some of the reasoning tasks for these simpler versions of OWL are of less complexity. So they are even sub-polynomial or polynomial. So this is rather fast. And then, of course, on the other end, you also have OWL2 full, which is then, of course, or consists of OWL-DL syntax in combination with all the possibilities you have or inherit from RDFS. So, as you might already assume, OWL2DL still is decidable, but OWL2 full, again, simply because of the legacy of RDFS, is not decidable anymore. Okay. Let's have a look of what is in OWL2. So OWL2 is Schroik, so you need a few more letters here. So first, let's have a look at the possible class expressions. Of course, you have class constructors like conjunction, disjunction, and negation. You have the existential and the universal property restriction, which stands for strict binding and loose binding. Then you have a concept which is called self, and you can define classes for which you can define a restriction which holds for all members of the class in relation. So you define a property in which they are related with themselves, so some kind of reflexiveness. Then you have the possibility also to define number restrictions, but in addition to the number restrictions from the previous version, OWL1, you can in addition also bind the range of a property to a specific class, including a number restriction. We will see what you can formulate and define and design with that. And of course, you have also the possibility to define closed classes or enumerated classes. For the properties, we have some special kind of properties. We have so-called simple properties. We will talk about that when it comes to the so-called general class inclusion. You have inverse properties, and you have a universal property, which is something like the counterpart in the properties to the so-called top concept that you have, to the universal concept that exists as a class, for which all classes are subclasses of, and which is not subclass of any other class, and the same exists here for property hierarchies. You also have a universal property, one for data type properties, one for object properties. We will talk about that soon. So let's have a look at the T-box. There you have axioms about class inclusions and about class equivalencies, and in the R-box, so the property axioms, there you also can define property hierarchies, and you have a new construct which is called general class inclusion. This is pretty interesting because here you can define complex properties by joining somehow simpler properties. So for example, you can define an uncle simply by stating that the uncle is nothing else but the brother of my father or the brother of one of my parents. So you have parents and brother as two properties, and out of that you can form a complex property. So this is general class inclusion. And then of course you can here, for example, define restrictions for your properties, for your roles. You can say they are transitive, they might be symmetric, reflexive, irreflexive, and you can also make restrictions about disjunctiveness. And in the A-box, in the assertional knowledge, you can make assumptions about class membership, about property relations. You can negate property relations, and again, equality and inequality. But we will talk about that in detail in the course of this fourth lecture. So, of course, we want to write OWL. And for that, OWL provides several syntax variants. So they are different. So first of all, there is a so-called functional syntax. So this substitutes the so-called abstract syntax of OWL1. This is rather short, rather brief, but in the end, I will give you an example, but we won't use it anymore. It's the same like the XML variant of RDF. So there is also an RDF XML syntax for OWL, simply for legacy reasons, and extends the former RDF XML syntax. And then we also have a so-called OWL XML syntax, which is an independent XML serialization of OWL. And there is something, we might come back to that later, it's the so-called Manchester syntax. In the Manchester syntax, that's a machine-readable syntax that is especially designed for or especially used in ontology editors. We will see that later on. This is also rather concise. And of course, there is a turtle serialization, which will we use then later on in the course of this lecture. So this will be then our kind of serialization. We have already learned turtle, and we will focus later on also on turtle with OWL. So here is a rather brief example of the functional syntax. So first, please look at the description logic definition in gray that is here above the box. So I define simply a happy person is somebody whose children are happy persons. And I do this a little bit more complicated because on the first part of the definition, I say that all of the children of somebody must be happy persons. And in the second part of this conjunction, I say that there must at least exist one child which is a happy person. Why do I do that? Simply because, for example, if the person I'm talking about doesn't have any children at all, nevertheless, the first condition, so the strict binding, would be fulfilled. Because if no children is a happy person, and if there are no children, then of course all of these children would be happy persons. So to define a restriction like that, that you say all of the children of somebody must be happy persons, then you should take into account that there should be at least one children. Otherwise, you would have also childless persons within your set, in your class you define here. So this is an interesting aspect that you should also or always consider when designing classes like that. So a happy person is a person who has happy children, or whose children are happy persons. So let's have a look at the functional syntax here. So what I do here is I define an ontology, and then here I also use these usual braces, and then I define a class. So I have a declaration of a class happy person, and then I define here an equivalent class axiom. So I say equivalent classes, and then the first one is the happy person class, and the second half then is this conjunction. This is the object intersection of. So it's the intersection that you see here. So a conjunctive constructor, and the first one then is the strict binding. So this is then the keyword object all values from applied on the property has child, and the range restricted to happy persons. And the same then for the existential quantification, the loose binding. This is then object some values from has child and happy person. So this would be the functional syntax. It's easy to define. There are no RDF restrictions given in there, and it's more compact, but we won't use it. So you have seen it, you can forget it. The next one would be the extension of the already known RDF XML syntax. So you know already this kind of serialization. Of course, here you in addition have to, for example, add namespaces for OWL, that you have also the OWL vocabulary that you can use here in your XML serialization. But as you might expect, of course, then these definitions blow up simply because of the properties of this RDF XML syntax. The next one here is the OWL XML syntax. So this is a specialized version of XML serialization of OWL with a completely new vocabulary, which is also defined here in a special namespace. So here is no XML namespace needed anymore. And the point is, okay, we won't use it, at least not for our lecture. So you've seen it, you might forget it. This one is more important. This is the Manchester syntax example. And as you see here, this is even more compact than the others we saw here. So it's like in the functional syntax, you define an ontology. And the first thing what you do here is first you define here rbox property. Then you say an object property you define here has the name has child. And you define a class happy person. And then you have an axiom. So this is equivalent to, means your class happy person is equivalent to. And then to these conjunctive connection of these two property restrictions. So first, has child is restricted to only happy persons, which is the universal quantification or strict binding. And then has child is restricted to some happy person, which is the existential quantification or loose binding. So you see here, this is much easier. You need much less characters, so much less space. So Manchester syntax is quite interesting. But of course, we will only use it then when we are talking about ontology editors, like for example, when I will give you later on examples with a protege web editor, for example. Okay, and here is the most important example of all. This is the turtle syntax example, and we know already turtle, so here we define a class which is called happy person, and we say this is an equivalent class, so this is already OWL syntax that we will learn very soon, and this is equivalent to another class which is here given in square braces, and of course this exists or consists of an intersection of these two restrictions on the property has child and then on the range happy person. First one with all values from, last one with some values from. But considering or concerning the special vocabulary that we need here in OWL turtle, we will talk about that in the future parts of that exact lecture number 4. So now you have got a first expression about OWL and the OWL syntax, and in the next part of the lecture you will learn about OWL classes, properties and individuals.